pushed this, I really expanded the user of this technique. So they have a company and they will sell a commercial instrument. They come in and set it up in your lab in a week or two, and you're ready to take this type of measure. They will just charge you 3 times as much as you would pay for the instrument yourself. Okay? But a lot of times it's still worth it. So this is, I think, because of their contribution, it's becoming a much more expanded tool. So these are raw spectrons. So this is what's called the driven spin wave spectron. So I can have a microwave, I can drive a particular spin wave mode, and then this spin wave have an indefinite lifetime. So these spectrons, this is the Rayleigh light, and this is the anti-Stowe peak, this is the Stowe peak, this is anti-Stowe peak. The line width doesn't mean anything. The line width of this peak is just the instrument resolution, because the spin waves are driven, they live on forever. And so both of these are taken on a permalloy nickel iron thin film. So this is driven spin wave. You spend 2 minutes, you get these very large signals. But as I said, magnon exists thermally. They're thermally excited. So if you don't have any microwave applied, you would also get a magnon spectrum. Looks very odd. It's because you actually have different frequency magnons that you're detecting. You're integrating from different wavelengths, different frequency magnon. This is what you get. The spectrum is what you get. So here's an example how I can use this technique to study spin waves emitted by an oscillator. So same, the same group have, the commercialized the BLS measurement, have done this nice work where they are injecting spin, electrical current, creating spin waves that are emitted from the tip, and now they use this optical probe. So what these images are, this image is the color contour is corresponding to the amplitude of the spin wave. So they can really study how spin waves propagate that are generated by a particular tip. So these are the raw spin wave spectrum. They typically integrate over a particular mode and generate spatial mode like this. So because of this type of study, they were able to design structures where spin wave, nano oscillator can be effectively phase locked together. Okay, so here's another example. So this is one of our early work that we launched a spin wave using a gold antenna. Let the spin wave propagate a magnetic waveguide, but we intentionally create a defect. And then the spin wave, supported by the waveguide, have several discrete modes. These are standing spin waves in the transverse direction. They propagate along the waveguide. And these are the calculated mode. And now this is the measurement, right? So we can take a particular mode and measure how this magnon propagate. So just like all waves, it goes through diffraction. This is a propagation when it encounters a defect, it goes to a higher order mode through a wave diffraction pattern. So this is more or less what you'd be expected from any wave, but spin wave is different. So what is different between spin wave than photon, for example? So first of all, many magnetic structures, multi-layer structures, break inversion symmetry. And as a result, there is a non-reciprocal property, meaning spin wave propagate in one direction and propagate in opposite direction have different properties. And they're highly nonlinear, meaning that the magnons are amplitude dependent. So if you make a very strong, intense magnon mode, and the frequency and velocity may change, maybe amplitude dependent, and due to magnon-magnon interactions. And when you have small structures, this kind of nonlinearity is even more pronounced. And of course, actually, nonlinearity is a necessary condition if you want to do any type of wave-based computing. Okay? So, and they're also highly anisotropic. As we know, magnetic materials are very isotropic. That is to say, when we establish saturation magnetization with external field, then magnon propagate along the field and perpendicular to the field have different frequencies. Therefore, having magnon turn a corner is actually a hard thing to do, because as it starts to propagate in a different direction, it would needs a different frequency. So actually, it's difficult to manipulate spin wave because of this. So these kind of anisotropy, non-reciprocal property of the magnon has been studied in a variety of different geometries. So, and with that, I finished the second part of my lectures about, how do we detect magnons. So let's again take a few minutes break, and let me see if you have any questions. Yes, please.
So you say that it's hard for it to kind of turn any corners, just kind of on the isotropic standpoint. So if you had sort of an easy axis that you're able to kind of shape around a contour, would that kind of allow for that propagation better?
That's exactly what you need. You need some in-plane gradient, right? So sometimes people can impose that kind of in-plane gradient with a current flow in a particular geometry, and they will have create some in-plane gradient that allow the spin wave to turn the corner.
Thank you.
Yeah. Great idea. Yes.
I'm curious that you showed two graphs about the driven magnon and the thermal magnon, right? So like when you do the like a BLS test, you can actually like separate them these clearly, or does that do they just couple to each other? You have to do some analysis to separate them.
Right, so in this type of spectrum, I do not see the coupling between the magnons. So all I'm doing is I'm taking the integrated measurement. So I have my photon come in, I'm just waiting for a scattered photon to come out, and I accumulate this scattered photon. So there is a shape, part of it is, determined by the magnon dispersion, or density of states.
Okay, thank you.
For the magnons.
Thanks. So how can we extract the magnon lifetime from this BLS spectrum?
So excellent question. So a lot of time we can't, because typically lifetime is encoded in the spectral width, right? A narrow width, for example, this one is infinite line width. The width becomes my instrument limitation. Any experimentalists know we cannot measure anything to infinite accuracy or precision. It's because any instrument has a limitation. So this is instrument limit. This is an excited magnon that should just live forever. It's like driven oscillator. And the thermal magnon typically, if you have an isolated mode, then you actually can't read out the lifetime through the line width. But in this case, this is a thin film. I just have too many magnon modes with frequency close to each other. So I have many overlapping magnon mode here. So again, I'm unable to extract the line width, to extract the lifetime from this. And that's another reason why people would do ultra-fast experiment, is because there you can actually resolve the dynamics. You can monitor the dynamics, magnon dynamics in time by changing the delay between multiple laser pulses. Okay. So it's not the perfect tool to study magnon lifetime. But what I can do is actually monitor this propagation distance, right? So I would be able to map how long the magnon propagate in a waveguide. So that's an important parameter to understand, can I can I use the magnon to do some devices? I should say this data has a decay divided out. So in a permalloy film, a magnon only propagates about a micron. And this propagation distance depends on the thickness of the film as well. But overall, you're not expecting it to propagate far more than a few microns. Okay? That's different in insulator. In an insulator, many people study YAG here, right? So I would guess a quarter of the people in this room have studied YAG. One of the reasons people love YAG is it has very low damping. You can have very long magnon propagation distance. It's used in a microwave circulator, right? For that reason, because it sustains a propagating mode well as an insulator. Okay. Other questions? So just quickly walk through, I told you how we detect magnons and really kind of focus on this inelastic light scattering process. Show you a few examples how we map out magnons in devices using the inelastic light scattering. And again, this picture, I divided the exponential decay function. The decay length is only a micron. And by the way, this is the intensity of the Magnon mode. And what I did is take this driven Magnon mode, I integrate the photon count underneath it, and I do a spatial mapping. This it's what I told my student warm-up project, but this data is actually 24 hours integration time. So it's a painful experiment because I'm waiting for the photon to count, right? So these are single photon detection experiments. The efficiency for the photon to scatter, create a magnon or annihilate a magnon is actually very low. So, but they now become a very standard technique in many laboratories. Other comments or questions? Yes, please.
It's a big question just about like a comparison to like, for example, Moog in this time. There's also like very long iteration times and all that. Can you like a quick comparison just for me?
Right, so Moog measurement and BLS measurement are all using light to probe the magnetic material, but they probe it differently. What Moog does is to probe the rotation of the polarization, right? So it's a static measurement. It measures the static. You get a more contrast. You don't actually measure a particular dynamic mode. You measure the typically you do longitudinal mode measurement. You're picking up the magnetization component perpendicular to the film, and then when you have light circular, when you have light focus on one domain versus the other domain, the polarization rotation is different. That's how you get a contrast. Okay, so but BLS light scattering is focused on, has a frequency component associated with it. So it's measure a particular collective mode, measure a particular Magnon mode. So you need both. If you want to understand the dynamic, if you want to understand the static property of your material, you do both. But if you want to understand the dynamic, anything is changing, you do light scattering.
Okay, I actually thought about TR Moog in that case, but
yeah, TR Moog. Okay, sorry. So TR Moog. So you're measuring, you're picking up the magnon by scanning the delay between pump and probe pulses, right? You see an oscillation. The oscillation period is the frequency. You do the inversion. The frequency is the magnon. So if you ask what is better, depends on what you're trying to do. With TR Moog, you're perturbing the material strongly. So if you want to understand what is magnon is doing in a device, not creating a large amplitude magnon, then you don't want to use TR Moog. What ultrafast experiment is good for, particularly good for, is to create a very large amplitude of a particular mode. Right?
okay, thank you.
Yeah, so we can, it's a long conversation,
Yeah.
but you can certainly pick up the mode. Any other questions? But TR Moog is better for measuring damping and lifetime. Question? Yeah.
As you talk about the different instruments which are used for detection of the spin waves, so sometimes my other question is about the sensitivity of the different instruments. Like sometimes you want to excite some exchange dominated spin waves, standing waves, but your instrument has a limited sensitivity because of the first order mode can be excited, but second and third order mode cannot be excited. So based on that, like which instrument which we more efficient to excite higher order modes standing waves?
Right, so the light elastic light scattering is not an excitation mechanism, it's a probing mechanism. So what I find that it really complements some of the the technique you're talking about, transport measurement you're talking about. I read a lot of literature where they just say it's magnon without specific experimental evidence that is actually magnon, right? So I think it's complementary to transport measurement. It's not an excitation mechanism. It's a probing. It's a way to probe it. So we still need to excite them electrically or using some devices structure to do so effectively. Okay. Any other questions? Okay, we're doing well, and now I'm going to talk about something that is relevant to some of you. So basically, we wanted to talk about how we apply these type of tool to assist in searching for better material or better conditions for creating skyrmions, right? A lot of you work with skyrmions. So one of the things that people need to stabilize small size skyrmion at room temperature is a large Jelanshinsky-Marie interaction. We heard the talk this morning where the speaker is a theorist, and he said that a lot of problem is yours, not mine. He also commented on there's very few serious measurement to try to understand interfacial properties, right? So this is I want to show you how we can actually use light scattering to actually extract interfacial term to search for condition that optimal for skyrmion formation. Okay? So I'm going to skip some introduction slide, but it's mind-boggling every minute of the day how many things that are happening that has to do with magnetic memories. I'll skip that entirely. And of course, a long history of magnetic memory evolutions. And we're at the point we're desperate for new ways to make more stable and smaller magnetic memory devices. One of the things we've heard earlier today is domain wall, racetrack, race memory. But skyrmion is another thing that has been proposed that perhaps can be used for magnetic memory. It's really interesting how the field of skyrmion has developed very fast. One of the early work in skyrmion work on these bulk material break inversion symmetry where they have found skyrmion using very elaborate tools at low temperature. But quickly we know that we can find skyrmion at room temperature in very commonly available magnetic material. So we all learned that when we write down the Hamiltonians, a lot of time we only write exchange coupling. It depends on the sign of that exchange coupling. We either a ferromagnetic order where spin are parallel or anti-parallel are favored. But of course, nature is far more complex in many material that with non-collinear magnetic geometry. Of course, certainly in the case of skyrmion, you also need a different term in the Hamiltonian that favors the a canted or orthogonal spin orientation. So whenever you have a situation you have skyrmion, you must have both terms. So the skyrmion itself is named after this gentleman. This is one of the early compounds where skyrmion is found. And then quickly, the people have learned how to blow skyrmion bubbles, right, through a magnetic restricted structure. These are Moog measurement, so you can actually see skyrmion forming and moving. And then, of course, now we know how to use a current to generate skyrmions and have them propagate. So this is already quite a few years old. But the question is, what kind of interface would favor skyrmion formation? So I have a colleague at UT Austin who always say that abuse the term DMI interaction. Jelanshinsky-Marie interaction was a term that was proposed in the 60s to explain a very weak ferromagnetic property in the antiferromagnetic bulk material. In those situations, the DMI term is typically about 1% of the J constant of the exchange term. So when we start to work with these magnetic bilayers with a ferromagnetic metal and with a heavy metal, heavy metal, non-magnetic heavy metal, so it's found that this kind of structure can have many uses, including hosting room temperature skyrmion. When we characterize the D term, the DMI term, compare them to the J term, exchange term, the DMI term could be about 30% of the exchange coupling. So it's really a very large component. So how do we actually measure the interfacial coupling terms? So how do we quantify the D terms? So one of the things you do is you measure spin waves, you measure skyrmions, and you measure spin wave dispersions. So this is light scattering BLS measurement. So one thing to appreciate is when light shines on the magnetic metal that's absorbing, only the in-plane momentum is conserved. And now, with the presence of the DMI term, the spin wave propagating in one direction versus the other direction have different frequencies. This is non-reciprocity, right? So, and then instead of having a symmetric spin wave, you would actually have a spin wave dispersion that's shifted. And the consequence of that shifting is that spin wave propagate in one direction versus the other direction. Even when they have the same wavelengths, they will have different frequencies. So this is highly unusual if you are familiar with Raman spectrum, because oftentimes you only measure the Stokes side. You just assume the anti-Stokes side had the same information. But in this particular case, you can actually see the blue and red curve. I'm reversing the in-plane magnetic field applied to change it to a different direction. So let's just look at the blue curve. So you can see actually the anti-Stokes peak on this side is slightly below 5 gigahertz, but the Stokes side is slightly above 5 gigahertz. So the Stokes side, anti-Stokes side have different frequency. It's precisely because of this this asymmetric spin wave dispersion caused by an interfacial interaction. So this is an example. I can do a light scattering experiment and measure the magnon pocket in one direction and versus the other direction, and measure the frequency difference between the two. Use that to quantify the magnitude of DMI, interfacial interaction. Okay, let me let you look at this for a little bit. So depends on, why would I be able to associate anti-Stokes peak and Stokes peak with different propagation direction? And that's because if I consider light, incident light and backscatter light, there's some momentum changes between the backscatter light. And that momentum is given to the magnon, okay? And it's given to the magnon, and if I probe this anti-Stokes side, I'm probing the annihilation of a magnon, then that corresponding magnon propagate in one particular direction to account for that momentum conservation requirement in inelastic light scattering. But if I look at the anti-Stokes, I'm actually, the photon loses energy, I'm actually creating a magnon, and then that created magnon must have a different in-plane momentum to satisfy that momentum conservation requirement. So this is all consequence of a momentum and energy conservation. So now I can look at the frequency change and use it to quantify DMI interaction. So, okay, so this is a measurement. Sorry, this is a little screwed up here. So where we actually look at the interface between a coffee bead ferromagnetic material and the irradiant manganese, which is AFM material, we can quantify the DMI interaction between these two layers. And because this is an interfacial effect, DMI term depends on how it's defined, it's actually becomes stronger for thinner film. Okay? So this is 1/T, so the thinner film is on the right side. The smaller 1/T is over here. So the DMI term is stronger for thinner film, for interfacial effect. And this says that the frequency shift between the Stokes anti-Stokes peak is linearly proportional to the momentum of the magnon. So I'm looking for an equation here. Here's the equation for the spin wave. So spin wave depends on the applied field, depends on the the wave vector of the spin wave is change constant, and then there's an additional term if you break the inversion symmetry in a bilayer structure, where this frequency changes linearly with the in-plane momentum. This D is the constant, is the DMI constant we're trying to calculate. So we're trying to extract. So therefore, I have a frequency shift that's linearly proportional to the momentum. Okay? So how do I vary the momentum of spin wave? I actually tilt the light relative to the thin film. So when I tilt the light relative to the thin film, the backscatter light have a different, momentum loss in the light scattering process. Through that, I can actually probe spin wave with different momentum. This is what I do. Again, keep in mind, light scattering process satisfies both energy conservation and momentum conservation. By tilting the sample relative to incident light, I'm changing the in-plane momentum of the light. In the backscatter geometry, is the change in the momentum is the twice of the in-plane of light. That determines what momentum I give to the magnon. So I can actually choose what is the wave vector of the magnon I'm creating or measuring. There's a lot in this slide, so I'm just going to pause here for you to take that in a little bit and ask questions if you like. Yes, please.
So how strong is the applied magnetic field?
So the magnetic field is, again, it's a, I didn't have the number written down, but it's on the order of 1,000 Worsted. All I need to do is saturate the magnetic thin film. So it's for these coffee bead, you don't require a very large magnetic field.
So you only operate with the saturated?
Yeah. And then, what I'm really looking for is the frequency change between spin wave propagating in one direction versus the other direction. For that quantity, is this term here. It does not even depend on external magnetic field. Okay. Yes, please.
Is there any way to calculate A and B simultaneously?
Yeah, so actually, yes. So this also offers a way to extract exchange constant. A lot of times, such a simple basic parameter is not easily extracted. People do a temperature-dependent, measurement to extract exchange constant. But exchange constant, you should expect it to be temperature-dependent. At a particular temperature, you should have a certain exchange constant. When you vary in temperature, you expect a different exchange constant. So this is indeed a convenient way to measure spin wave. Is a convenient way to extract exchange constant. So now we're getting into what do I use this magnon measurement for? If I don't want to build a spin wave computing, if I don't want to build a oscillator, there's many other ways this light scattering measurement of magnon can help me in other ways. So this is one example. It allows me to measure some very fundamental properties in magnetic thin film and bilayers. So we literally will get these films that people grow this film with a wedge thickness, and they will give it to us and tell us where to find a skyrmion. Then we will do these kind of light scattering experiments and say, this is where you want to look. And they would find the skyrmion there. So this is one of the things we did that was actually useful. I don't do many useful things in my own research, but this is one proud example. Yes.
So, the first half of that equation there looks a lot like the Kittel
Yes.
equation. So
It's exactly the Kittel equation.
Right, okay. But with this modified a k squared term, which is the exchange constant and
Yes.
the wave vector.
That's right.
Oh, okay.
Yeah. So the spin wave equation can be even more complex. Depends on, sometimes anisotropy must be considered. Here I actually take a simple form because most of the other term would not depend on the direction of the wave vector. So I just drop them and leave a few things that are critical for you to see.
Okay, thanks.
Yeah. Yes.
I have a question about theta.
The theta, yeah.
Yeah, so typically when you do the experiments, you have
to change the angle
Yes.
to find an optimal like angle to get the signals, or
So that's not what I use it for. So I forgot to explain this little piece. So this is if I take 2 pi over lambda, this is the wavelength of my light, right? I need to put an epsilon somewhere there to give you the wavelength of light in the material, okay? And now I take times sine theta. If you look at this, when I times sine theta, I actually get the in-plane component of the light. So the in-plane component is conserved in this light scattering process. And then when I detect the backscatter light, it actually have twice of the incident light in-plane component. I've lost that momentum. Where did that momentum go? It was, given to the magnet. So this is how I know what wave vector of the magnet I'm actually detecting. Okay? So you also notice these spin waves are pretty well behaved. They're thermally excited magnons. I'm not exciting them any other way. These are thermally excited magnons, but have a very well behaved resonance. And in fact, the line width even changes with the damping of the film I'm measuring. This is one of the cases that the line width is correlated with the film damping. So the reason I want to change the incident light in this particular case is because I want to map out how the DMI introduced frequency change vary with the Magnon wave vector. So this is what I use it for. So this will allow me to get a more accurate measurement of the DMI term. Some people don't like to do this. They just take one data point and they assume that the DMI will go to 0 term. So certainly, we do this, we vary the incident angle to get many data points so we can fit a linear term for that Magnon frequency shift. So as you all know that the magnetism in a lot of devices is really complicated, right? I actually need to compare different type of interface. So this would allow us to give a more predictive, we're not doing theory, but we can inform other people who are making skyrmion devices what kind of a combination of heavy metal you will use, and we even compare that with topological thin film. To be honest, we don't know whether this is still topological, because the surface state is easily damaged. It took people a long time to figure out how to grow these topological insulator, embed them in with a magnetic thin film so that you can benefit from that. So this is an example how we can use this type of measurement to quantify interfacial DMI effect to guide the search for skyrmions, or even perhaps understand how do you compare that with the calculation. Okay? Yes, please.
So if we can test positive DMI,